Here we are presenting our new ICCV paper called Meta-OOD Learning for Continuously Adaptive OOD Detection. First of all, let us review existing OOD detection if you are not familiar with it yet. Basically, the classic machine learning model assumes a closed-word setting, meaning that the training data and the testing data share the same label set. However, as shown in the diagram, this is not so true when we want to deploy the ML model to the real world, because it will inevitably encounter unseen and unknown data that was not included in the training set. This data is what we call OOD data. Modern deep learning model tends to make overconfident predictions on this OOD data, which is not trustworthy. That's why OOD detection was proposed, aims to alert the ML model about OOD testing samples while maintaining the model's ID samples accuracy. Existing OOD detection assumes that both ID and OOD samples are drawn from static distributions. However, in the real world, the systems are often changing dynamically and shows continuous distribution shifts over time. Here is an example of continuous shifting distributions. Let us imagine that we're driving a car on the road. The illumination and the weather condition could change dynamically and continuously. Therefore, to promote OOD detection's application to the real world, we are motivated to propose a new problem called continuously adaptive out-of-distribution detection. Basically, CAOD aims to train a good initialized OOD detection model such that during the deployment, the model can quickly adapt to newly arriving distribution with insufficient testing samples. And in this process, the model could maintain both ID classification accuracy and OOD detection effectiveness. In this paper, we proposed a method called Meta-OOD learning to address the CAOD problem. Let us formulate a classification model F as a function composition of a classifier, an adapter, and a feature extractor. To address fast adaptation with insufficient ID samples during testing, inspired meta-learning technique, we propose a meta-training process that is specifically designed for continuous domain adaptation. As a result, during the deployment time, we only need to update the light-weighted adapter and classifier by a few steps with insufficient testing data. Also, because we don't have access to OOD samples during the training process, we propose to generate OODs for regionalization. To do so, we firstly model the class condition distributions on ID data, and then we sample OODs from the estimated ID distribution. For the experiments, we evaluate our method on 3 COAAD benchmarks. To apply the static OOD detection method to the CAOD problem, we use 3 different adaptation schemes. The experimental results show that our method improved greatly on both ID accuracy and OOD detection performance, showing the effectiveness of our proposed MOL. When we check the performance at each testing distribution, the purple line marks our method. It shows that our performance was maintained while other OOD detection performance dropped heavily over time. Also, theoretically speaking, modeling in continuous time interval requires infinity samples, making it unrealistic. As such, discretization is a common way to address continuous adaptation. So we analyzed the impact of discretization by evaluating our method on 10 randomly sampled testing distributions. The table shows that the average performance remains stable across various trajectories. Thank you for watching this video. For more details, you may refer to the full paper and supplemental materials. You may also reach me via the email.